Properties of water. Looking back on Earth from space, an astronaut called it the blue planet, referring to the oceans of water that cover nearly 3/4 of the Earth's surface. The very presence of liquid water tells a scientist that life may also be present on other such planets. Why should life itself be connected so strongly to something so ordinary that we often take for granted? How does the molecular structure of water contribute to its unique properties? Water is a polar molecule. It is able to form multiple hydrogen bonds, which account for many of the water's special properties. So on this one, there's a partial negative charge on the top because of the shared electrons. They pull an electron, oxygen pulls an electron from the two hydrogens to share. It makes a small negative charge here, not a full charge, just a small one, and then a positive on the other end of the two hydrogens, and they're off balance. The positive and negative partial charges come from the fact that these two pair and these two pair, and there's two more remaining pairs, form a tetrahedral shape, not opposite. They can't form opposites because the tetrahedral is in 3D. Water is one of the few compounds found in liquid state over most of the Earth's surface. Like other molecules, water, H2O, is neutral. The positive charges on its 10 protons balance out to the negative charges of its 10 electrons. Because of the angle of its chemical bond, the oxygen atom is on one end of the molecule and the hydrogen atoms are on the other end. With 8 protons in its nucleus, an oxygen atom has as much strong attraction for electrons than it does a hydrogen atom with a single proton. In the tetrahedral shape, there'd be 2 orbiting electrons here and then 2 in the back as a tetrahedral 3D shape. There is a greater probability of finding the shared electrons in the water close to its oxygen atom than near the hydrogen atom. As a result, the oxygen end of the molecule has a slightly negative charge, and the hydrogen end of the molecule has a slightly positive charge. A molecule in which the charges are unevenly distributed is said to be polar because the molecule is a bit like a magnet with 2 poles. The charge on a polar molecule are written in parentheses, the negative and the positive, to show that they are weaker than the charges of ions such as Na plus and Cl minus, which form a much stronger ionic bond. So in this hydrogen bonding with this molecule that now is polar, because the partial charge, positive and negative, polar molecules, such as water, can attract each other. The attraction between a hydrogen atom on one water molecule and the attraction to the oxygen end of that other water molecule is known as a hydrogen bond. Water is able to form multiple hydrogen bonds, which account for many of its special properties. Hydrogen bonds are not as strong as covalent or ionic bonds, and they can form in other compounds besides water. Cohesion is the attraction between molecules of the same substance. Because a single water molecule may be involved in as many as 4 hydrogen bonds at the same time, water is extremely cohesive. So one here, one here, one here, and then one here. Cohesion causes water molecules to be drawn together, which is why drops of water form beads on a smooth surface. Cohesion also produces surface tension, explaining why some insects and spiders can walk on a pond's surface. Adhesion is an attraction between molecules of different substances. The surface of water in a graduated cylinder dips slightly in the center, forming a curve called meniscus. Because the adhesion between water molecules and glass molecules is stronger than the cohesion between water molecules. Adhesion between water and glass also causes water to rise in a narrow tube against the force of gravity. This effect is called capillary action. This capillary action with a larger tube is not as strong, smaller tube, and in even a smaller tube, the capillary action rises against gravity, will pull up this water because of adhesion. Same effect happens in a tree in these tiny capillaries. And here we see adhesion, the water droplet is stuck to the leaf, and in cohesion, water holding itself together. Capillary action is one of the forces that draws water out of the roots of a plant and up into the stems and leaves. Cohesion holds the column of water together as it rises. Water also is unique because it has heat capacity that is quite high. Because of the multiple hydrogen bonds between water molecules, it takes a large amount of heat energy to cause those molecules to move faster and raise the temperature of water. Water's heat capacity, the amount of heat energy required to increase its temperature, is relatively high. Large bodies of water, such as oceans and lakes, can absorb large amounts of heat with only small changes in temperature. This protects organisms living within from drastic changes in temperature. At the cellular level, water absorbs the heat produced by cell processes, regulating the temperature of the cell. How does water's polarity influence its properties as a solvent? Water's polarity gives it the ability to dissolve both ionic compounds and also other polar molecules. So water is not always pure. It is often found as part of a mixture. A mixture is a material composed of two or more elements or compounds that are physically mixed together but not chemically combined. Living things are in a part composed of mixtures involving water. Two types of mixtures that can be made with water are solutions and suspensions. If a crystal of table salt is placed in water, sodium and chloride ions on the surface of the crystal are attracted to the polar water molecules and they'll break apart. So the NaCl, each of these will then be surrounded by water. A sodium atom and a chlorine atom will be separated and surrounded by water. Ions break apart from the crystal and are surrounded by the water molecules. The ions gradually become dispersed in the water, forming a type of mixture called a solution. All the components of the solution are evenly distributed throughout the solution. In a saltwater solution, table salt is the solute, the substance that is dissolved. Water is the solvent, the substance in which the solute dissolves. Water's polarity gives it the ability to dissolve both ionic compounds and other polar molecules. Water easily dissolves salts, sugars, minerals, gases, even other solvents such as alcohol. When a given amount of water has dissolved all of the solute it is able to dissolve, then the solution is said to be saturated. Some materials do not dissolve when placed in water, but separate into pieces so small they do not settle out. Such mixtures of water and non-dissolved material are known as suspensions. Some of the most important biological fluids are both solutions and suspensions. Blood is mostly water. It contains many dissolved compounds, but also cells and other undissolved particles that remain in suspension as the blood moves around the body. A suspension and solution. As particulate, you can see acids, base, and pH. Why is it important for cells to buffer solutions against rapid changes in pH? Buffers, dissolved in life's fluids, play an important role in maintaining homeostasis in organisms. Water molecules sometimes split apart to form hydrogen ions and hydroxide ions. The reaction can be summarized by a chemical equation in which double arrows are used to show that the reaction can occur in either direction. Water can become a hydrogen ion and also a hydroxide ion, or the hydroxide ion can combine with a hydrogen ion and become water. In pure water, about 1 water molecule in 550 million splits to form ions in this way. Because the number of positive ions produced is equal to the number of negative hydroxide ion produced, pure water is neutral. So an acid is any compound that forms hydrogen ions in a solution. A base is a compound that produces hydroxide ions, OH negative, in the solution. So the pH scale measures this. Chemists devise a measure system called the pH scale to indicate the concentration of hydrogen ions in solution. pH ranges from 0 to 14. At a pH of 7, the concentration of hydrogen ions and hydroxide ions are equal. Pure water has a pH of 7. Here we see strong acids, lemon juice, tomato juice, less acidic. Normal rainfall is still acidic, and milk, slightly acidic. Here we move to the basic side, human blood, a little bit basic, seawater, toothpaste, basic soap, ammonia solutions, stronger basic, and bleach, very basic, and oven cleaner, strong bases. Acidic solutions have a pH below 7 because they have more hydrogen ions than hydroxide ions. The lower the pH, the greater the acidity. Solutions with a pH of 7 are called basic because they have more hydroxide ions than hydrogen ions. The higher the pH, the more basic the solution. Each step on the pH scale represents a factor of 10. For example, a liter of solution with a pH of 4 has 10 times as many hydrogen ions as a liter of solution with a pH of 5. Acidic solutions contain higher concentration of hydrogen ions than pure water and have a pH value below 7. Strong acids tend to have pH values that range from 1 to 3. Hydrochloric acid, HCl, is a strong acid produced by the stomach to help digest food. Stomach acid, 1.5. A base is a compound that produces hydroxide ions in solution. Basic or alkaline solutions contain lower concentrations of hydrogen ions than pure water. Strong bases such as the lye used in soap making tend to have pH values ranging from 11 to 14. So, the pH of fluids within most cells in the human body must generally be kept between 6.5 and 7.5 pH in order to maintain homeostasis. If the pH is lower or higher, it will affect the chemical reactions that take place within the cells. One of the ways that organisms control pH is through dissolved compounds called buffers, which are weak acids or bases that can react with stronger acids and bases to prevent sharp or sudden changes in pH. Adding acid to an unbuffered solution causes the pH of the unbuffered solution to drop. If the solution contains a buffered solution, however, so this is unbuffered, add the acid, it would become acidic. A buffered base, however, already a base, adding an acid to that would only become more neutral or still a base.